Okay. Let's get started. Right. So we finished talking about energy dissipation, right? Which is all those things that take energy out of the system. So we're not done talking about it, but we finished talking about friction and where it comes from and why it's there and how we figured it out, right? So Leonardo da Vinci did most of that work. We said that there's two types. There's a static friction and there's the dynamic, or we also call it kinetic friction. Either one of those names work. So we sometimes call it kinetic as well. Kinetic, which is why we put the little K, if you were wondering about that. And kinetic friction keeps objects moving at a constant velocity, or tries to keep it moving at a constant velocity. The thing about static friction that I was not able to get to, or maybe I did say something, but I didn't say it too formally, was that static friction, whenever we use the equation here, did I write it down? Hold on. Yeah, this one here. So let me rewrite that. The force friction is equal to mu s times n. For static friction, let me write the little f there. Static friction, when we use this equation, this is the max that static friction can be. So really, frictional force will be less than or equal to mu s times n. So for example, we can have a case where maybe the max frictional force is 100, but I'm only applying a 50 Newton force here, all right? And so the F max, if F max is equal to 100, but I'm only applying a 50 Newton force, then whenever I do, let's draw this out. So we have the frictional force F sub F acting that way. Whenever I sum my forces in the X direction, right? And let's say that it's not moving. So my force in the X direction, I'm going to have a 50 minus F sub F equal to 0. And so my frictional force is actually going to equal to 50 Newtons. So it can be up to 100, but it doesn't have to be 100. It's going to depend on the other forces acting on the box. Now, if I have 150 Newtons acting on the box, I'm pushing with 150 Newtons, that exceeds the frictional force for the static frictional force. And so I'm no longer using static friction. I'm using kinetic friction at that point. Okay. So the max it can be is 100 in some situation. So it can be up to that. It can be from zero, anywhere from 0 to 100, a 0 to 100 force, I guess. I hope that makes sense. This is the max it can be. It can be anything less than that. If it goes over that, then it means the box is now moving. And hopefully you all saw that in the lab that you guys did for the forces and stuff. This one, let me open it up. Where is it? Here. So let me share that real quick. Continue. We want this one. Okay, for this guy. Right, so as I applied the force, let's put values in. As I apply this force, right, you'll see that the force of friction is going to be equal to that 34 Newton force. until I get to some point where my applied force exceeds the friction force. See, all right, so now it's at 94 and now it starts moving. As soon as I pass that 94 newtons, it starts moving, okay? So I've exceeded the static force, okay? So you'll see that the static friction force, it increases until it reaches that point. I'm going to silence that. Hold on. Silence. Okay. So hopefully that, go back and play with that if you want to get a better understanding, or find some YouTube videos. If I'm not explaining it well enough, go and find some YouTube videos on that, because that's something that students tend to get a little bit confused on when to use the max friction and whatnot. So let me stop sharing there and go back to the tablet. And of course, ask me questions if you need more help on something. Okay, so that's friction. So let's see an example. Oh, viscosity and drag. Those are the other two. These are the other two that we need to look at. So let me go down. Friction is the one that we're going to see the most, but we do see these other two as well. So the first one would be viscosity. Viscosity. All right, and so this is another non-conservative force that steals energy away from our system. Okay. Viscosity is usually in liquids. Let's see, we can talk about both of these at the same time. And drag. All right, so we're dealing with like liquids, like water. Water is going to have a certain viscosity. Oil is going to have a different viscosity, and a lot of times we think of that as kind of a thickness of the liquid, and that does have something to do with how condensed all those molecules are together in a liquid. So viscosity is going to be in liquids. Drag is going to be in air. All right. Or gas, I should say gas. Okay. And both of these things oppose a motion in some fluid. So gases are considered a fluid because they flow. So anything that flows is considered a fluid. So liquids and gases are both fluids. They're different types of fluids, but they're both fluids. So whenever I say fluid, I mean either liquid or gas. So both oppose motion in fluid. All right. For viscosity, we have the equation, and we're not going to go through all the details of how it comes to that, but for a liquid, we have viscosity, the friction, or the force of viscosity. So we have a V, FV, F with a subscript with a V. So it's equal to negative B times V. So this B is kind of like our mu for the friction. It's a coefficient. So this is called our coefficient of viscosity. Why they picked a B, I don't know, but they did. And V, of course, that's going to be our velocity. So the greater our velocity is in a liquid, the greater our force due to viscosity, that viscosity force is going to be, right? Because B is constant. B doesn't change. So the only way to get a higher force due to viscosity is to increase our velocity. And then we have the drag force, and that's going to be equal to negative CV squared. And anybody who's watched things like Fast and the Furious and stuff knows what drag is, right? Anybody who's into car racing and stuff knows how important this one can be for vehicles and stuff, right? Whenever we're trying to gain speed, we want to reduce the drag on the car. We're trying to reduce the force of drag on the car so that we're not so that all the energy is used is to move forward. So for a vehicle, there's two things that we care about. There's the frictional force on the tires and the pavement. If we can increase that, then we get more speed, more energy going into moving the car forward. And then if we can decrease drag, then we're using less energy to fight that drag as well. All right. So those two are important in vehicles and cars. C, again, that's going to be our coefficient. Why they pick C, I don't know, but it's the coefficient of drag, or the drag coefficient, right? And so we want to reduce that as much as possible. Notice that in this case, our velocity is squared, so we still have velocity. This is still velocity. All right. So that means that if I double the speed, the drag is actually going to increase more. It's not linear anymore. Okay, so let's get an example here. Let's say, and this is old. I don't even know if this is, actually, I don't even know if this is real numbers, but Ford claims that the Fusion has a drag coefficient of 0.27. 0.27, yes. All right, so C is equal to 0.27. All right, and so let's just look at the velocities. Let's look at a velocity of 13.4, so 13.4 meters per second, and then let's double that. So our velocity, this is going to be situation 1, and situation 2, our velocity is 26.8 meters per second. So let's figure out what the drag is over here with the 13.4 meters per second velocity, and then again with the 26.8, see what happens with our drag. So we've got a negative 0.27 times our velocity squared. All right, and so when you plug that into the calculator, let me redo this because it looks like I made a mistake on my notes. 48 point, no, that's right, 48, I got 48.5. So negative 48.5 newtons. Okay. Now let's do it again for the V2 there, the 26.8, where we double our speed. That's going to be negative 0.27 times 26.8 squared. And that should get, let's see, I'm going to do it again. I got a 193, yeah, so 194, we'll say 194 newtons. All right, negative. All right, so the magnitude for the first one is 48.5. The magnitude for the second one is 194. If I divide these, so 194 divided by 48.5, I should get something close to 4, and I get exactly 4. Okay, so if I double the speed, I quadruple the drag. All right, so you double the speed, you quadruple the drag. So you can see if we really want to minimize that drag coefficient, if we want our vehicles to really take advantage of the energy that we're putting into it to go fast. All right, very important. Drag coefficient is very important for that. Okay. This leads us to our non-conservative work. All right, so non-conservative work is whenever we involve non-conservative forces, right? Let me see. It's got a similar, I put same here, but it really, I should say, it's got a similar definition for work. But using non-conservative forces, all right? So what are those non-conservative forces again? That would be friction, drag, or viscosity, okay? All right. Our non-conservative work is going to be work, NC. So we're going to use the subscript NC to stand for non-conservative, is equal to the negative, right? The negative, in this case, we're going to use frictional force. So the negative frictional force times delta X. And all this negative does is it tells us that energy left the system. Okay, that's all that does. That's what the negative's there for. So we come up with a work energy system. So we know that these things, well, let's work this out. We saw before we're going to take our equation that we had before where we said that work is equal to the change in E total, right? We did see that, right? Let me go back. Let me make sure I'm not pulling. Yeah, work and energy. Work is equal to no, we never discussed it. Yeah, we did. All right, it's right here. Okay. So work, now we're going to say it's non-conservative, is equal to our change in our total energy. Okay. Whenever there's no non-conservative forces involved, then the non-conservative work is equal to 0. All right. So then the E total is going to equal to 0. Here we're going to have, we found an equation for this. It's going to be a negative F sub F delta X is equal to delta K plus delta U. Okay. Another way that you can write this is just to use a lowercase f. So you can also write just like this, and people will understand that that's friction. So you can write it that like this as well. Just so you know, if you see that, and I might start using that just to keep it a little simpler. But both of these are the same thing, it's friction. It's force due to friction. Okay. Both of those are the same thing. And so if we expand this, then we have that negative F delta X is equal to KF minus KI plus UF minus UI. So anytime we see friction, and this can be substituted with drag as well. We just plug in our drag or our viscosity equations instead of that. So it'd be negative B times V or negative C times V squared, depending on what's going on. So if we were dealing with drag and friction, it would be negative F delta X minus C V squared, right? But this in generally speaking, this is what we'll use when we're dealing with non-conservative work. Okay, right. Right, and of course, when no friction, then WNC equals to 0, and then we have that delta E total is equal to 0, and so we have that we have Ki plus Ui equals to Kf plus Uf, which is our conservation of energy equation. So we're back to that again, right? So when there's no friction, there's no non-conservative force, then the non-conservative work is 0, and we get back to our conservation of energy equation. All right, let's look at this example. And I'll give you a couple minutes to write it down. All right. Example 3 says an 8-kilogram sled is initially moving at an unknown speed on a horizontal road. The coefficient of kinetic friction between the sled and the road is 0.40. The sled eventually comes to stop over a distance of 3 meters. Find the energy dissipated by friction, that's 1. 2, we want to find the change in kinetic energy of the sled, 2. And 3, what is the initial speed of the sled? So we're trying to figure out what B1 is. All right, so as usual, we want to draw, all right? It's very important that we draw stuff. All right, so we've got a horizontal road. We've got a box on that road. Right, that box is going to have a mass M. And it moves a distance of 3, what is it? It moves a distance of 3 meters. So we start here, it's going to move some distance, let's say right here, of a delta X equal to 3 meters. So that's the displacement, right? Right. We know that the mass of this thing is 8.0 kilograms. We were given a kinetic friction. All right. So kinetic friction means it's moving. So it's going to have an initial velocity there. It's going to work against the motion. So we have a kinetic friction mu sub K equal to, so kinetic and dynamic, again, those we mean the same thing there. And it says it's 0.40. We have, again, we have a delta X of 3 meters. The box is moving this way, and we have an initial velocity of we don't know what. We're going to end up, it says it starts, let's see, the sled eventually comes to a stop over a distance of 3 meters. So the final velocity is 0. So V1 equals to we don't know. B2 equals to 0 meters per second. And I think that's all the information that we have. All right. So we drew it out. We understand the problem. We see what direction things are moving, what the change, the displacement is, all that good stuff. We have everything that we need in a nice, concise little picture with all the values on the side so we know what we're talking about. To solve for one, it says the energy dissipated, all right? When we say dissipated by friction, we're meaning that it's taken it out. So somehow we need to figure out what the energy is for friction. That's going to be our work. So that's going to be our non-conservative work. And we're just dealing with friction. There's no drag, there's no viscosity. So we're just dealing with friction. So it's negative F sub F delta X. All right. So I'm just going to draw a free body diagram here. I'm going to have the weight going down and a normal force going up. All right. I don't have any force pushing this thing, so we're assuming that something gave it an initial push. We don't know what it was, but it gave it an initial push. But we do have friction acting this way. And again, I'm going to start using a little f for friction just to make it a little easier. So whenever I do this, so this is the nice thing. We're dealing with kinetic friction, so I just need to plug in the kinetic friction coefficient. Kinetic friction doesn't change like the static friction does. Static friction can go from 0 to whatever the max value is. Kinetic friction just stays the same. So friction, oops, good grief. Friction is equal to mu sub k times F sub n. Right, that's the normal force. So we need the normal force. So to find the normal force, I need to do the sum of the forces in the y direction. Up is positive. So we've got mg going down, so it's minus mg plus F sub n equal to 0. So F n is equal to a negative, what was it, 8 times 9.81. And that gives me a 78.48 newtons. Right, and so that we can plug back into our friction. That's going to be mu was 0.4 times that 78.48. So that should be 31.39 newtons. Okay. We have that. All we have to do now is plug that back into our work. Our non-conservative work is going to equal to that negative friction, 31.39, times the change in X, and that's just going to be 3 meters. So times 3. And I believe this was right. It rounds to about negative 94 joules. Right, so I'm just taking things that I already know. I already know how to do a free body diagram. I already know how to do some of the forces. We've done that in one direction. So I can figure out my friction. I plug that back into my equation. I've got work. All right, cool. All right, 2. The second thing we're supposed to do, I don't remember, what was it? Find the change in kinetic energy of the sled. All right, so we have an equation for that as well. We know we found this, right? We found that to be negative 94. And we know that the non-conservative work is also equal to the change in the total energy, which is equal to Kf minus Ki plus Uf minus Ui. So question, what are these? What values can we give those? What do we have potential energy in this situation?
No, because it's only moving towards the sides, not vertical.
Yeah, so we don't have any vertical change. There's no spring, nothing like that. So we have, we have no change in Y, and we have no spring. Okay, so both of these are going to be equal to 0. Right, so our non-conservative work is just going to be Kf minus Ki. Kf is going to be 0. 1/2 mv2 squared is going to equal to 1/2 times 8. What was our, I keep forgetting what our mass is. Yeah, 8 times 0 squared, that gives us 0. Ki is going to equal to 1/2 mv1 squared, that's 1/2 times 8 times times v1 squared. So we can plug that back in. We know, so we know this, we know this, and we found an equation for this. So this was -94. Kf is 0 minus a 1/2 times 8, which that just gives us 4. I'm just going to write 4. 4v1 squared. So we have v1 squared equal to 94 divided by 4. Take the square root, and v1, you should get that v1 is equal to 4.8 meters per second. All right, so that's just algebra at that point. Okay, so for this part, I need to understand what potential energy is and whether it's there or not, right? I need to know what kinetic friction, or not kinetic friction, kinetic energy is, and I need to recognize when I can use that equation. I know I can use that equation, one, because of the way it asked me the question, right? It said find kinetic energy. What's the kinetic energy of the change in kinetic energy? So actually, it's a change in kinetic energy. So we did kind of both parts here at the same time. So the change in kinetic energy is going to be just -94. I didn't explicitly write that, so we kind of did part 3 here. The change in kinetic energy, then, that's what this is, right? So the change in K is just going to equal to -94. So that answers part 2. This answers part 3. Sorry, I wasn't paying attention. Okay. All right. Any questions over any of that? Okay. So we've just got 2 more little things to talk about. Let's see, what time is it? Perfect. All right. So this power, I'm going to have to skip a little bit of story for power, where we got it from, how it was discovered, but just know that some guy named Watt, some guy named Watt got a horse and lifted up some 550 pounds and said how many, and just that was what he said as a watt, or horsepower. He called it horsepower. The power is defined as the derivative of energy with respect to time. Okay, so P is power, a capital P. Okay, so it's a capital P is power, is equal to the derivative of energy with respect to time. And so that's about equal to a change in energy over a change in time. The units are the joule per second, and we call that a watt. And again, that's after the guy Watt. He came up with how to measure power by coming up with horsepower. He actually called it horsepower. And you know what? I'm going to go ahead and talk about it. So what he did was he got a pulley, something like this, and a rope. Let's draw the rope in some other color. All right. And at the end of this rope, he attached a 550-pound block. And then he had a horse over here pulling that direction. And so what he did was he measured how fast a horse can lift 550 pounds by 1 foot. A 550-pound object by 1 foot. And he measured that time. And so he found this thing to be, he called this 550 pounds per second, and he called that 1 horsepower. Okay. And so he came up with that. So that's just the simple version of the story. I'm not going to go too further into that because I want to get to the last problem here. But just note that 1 horsepower is equal to 746 watts. So there again, we have another W, guys, another W. So we have work, we have weight, and we have a watt. Weight, I think it's safe if instead of writing a W for weight, just keep it as mg. All right, so there's no confusion. And that way, these other 2 W's, whenever we're dealing with work, it's a variable that stands for work, right? And then here we have a unit. This one's a unit. So keep those straight in your head. So for weight, for this, from this point on, just whenever you're dealing with weight, use mg. And then just remember for the other 2, even write them differently if you want. Like for a watt, write it as a kind of a very angled W, and for weight or for work, more curvy if you want. Just some way distinguish those things so you don't get them confused. Yeah, and I'll leave that to y'all to decide how you want to do that. Where's my example 4? Why isn't my example 4 here? I set this up. All right, let me copy this over. Oops. Okay, and sync, and there it goes. All right. Let's take a minute to write that down. Okay. It says a 670 Newton sprinter runs the first 7 meters of a race in 1.6 seconds, starting from rest. So our initial velocity is 0. at the end of 1.6 seconds, what are the sprinter's speed, kinetic energy, and power? So we got this guy and he's running. I'm going to draw a really fancy stick figure. And he goes a total distance of, right, so there's a displacement of 7.0 meters. At the start, he starts from rest, right? His weight is 670 newtons. So we know he's got a weight. He's got 670 Newton weight. That's right. mg is equal to 670 newtons. All right. And this is at a time equal to 0 seconds. At the end, you know, his weight doesn't change, obviously, but we have a final, let's call this T1. This T2, we have a final, he says 1.6 seconds. So in the span of 1.6 seconds, he was able to travel 7 meters. And that's all the information. All right, so A, right, we have to figure out the acceleration to figure out the speed. And where is my acceleration speed? Okay, there it is. All right, so hold on. Yeah, I can't do that. So we got to figure out what his acceleration is. To do that, we need to go back to our kinematic equations. All right. So to skip all some of this, I'm just going to give you the equation that's useful here. 1/2 AT squared, right? So I know this is going to be x minus x naught is equal to v naught t plus 1/2 AT squared. My v naught is 0. The change in x is 7. So it's going to be 7.0 is equal to 0 plus 1/2 a times 1.6 squared. And then just solve for a. And that's going to give you 5.47 meters per second squared. So we should know how to do that. So I'm not going to go too much into that part. And then the same for the velocity, we have to use our kinematic equations. So we're going to have v is equal to v naught plus at. So, I mean, obviously we can't forget this stuff because it follows through. Everything builds on itself in physics. You can't forget the first stuff just because we're in work and energy now, right? So you still have to use these things. We're looking for v, we're given v naught. So v is equal to 0 plus 5.47 times 1.6. So our final velocity v, and I should say v2, and this should be v1, but hopefully you guys can follow that. That's going to be 8.75 meters per second. So I kind of went through that one real quick. We should know how to do that by now. B, we're asked to find the kinetic energy. Well, that's pretty easy. Our K1, our initial kinetic energy, I said Ki, so K1 is equal to 0 because our initial velocity B1 is equal to 0. Okay, so K1 is 0, K2 is equal to 1/2 mv2 squared. That's going to be 1/2. We have to figure out m. So mg is equal to 670. Right? So m is just equal to 670 divided by 9.81. That gives us 68.3 kilograms. So I'm going to plug that in here. That's 68.3 kilograms times v. We found that to be 8.75. squared. So K2, that should give you 2,615 joules. And finally, see, it asks us for the power. So the power is just the change in energy over the change in time. All right. So P is going to equal the change in energy over the change in time. Well, in this case, we don't have potential energy. All of our energy is kinetic. So this is just going to equal to the change in kinetic energy over the change in time. All right. And so we found this. So P is going to equal to that 2,615 minus 0 divided by the change in time was that 1.6 seconds. So plugging that into a calculator, you should get 1,634 watts. Okay. And that's the end of our discussion on, well, for now, of work power and energy dissipation. Are there any questions? The last comment I might want to make is here's something that might be asked is, how do I know to use that? You have to look at your tool bag, right? Everything that we've learned is in our tool bag. We have to look at all the equations that we have and see which ones are useful for what we've got. I couldn't use kinetic energy directly, right? 1/2 mv squared, because I didn't know what V was. And I don't know what the kinetic energy is. I don't have any way of figuring out what the total energy is yet. So I can't use my kinetic equations. I mean, I can't use my energy equations. I can't use my force equations because F equals to ma. That doesn't give me velocity, and I'm looking for velocity. I could use it for, I could have used it to find acceleration, but I don't know what forces are acting on this guy, right? I have no idea what forces are acting on him besides, you know, it doesn't tell me outside of the weight. I don't know what forces are going on here, you know, between, you know, maybe his feet and the pavement or whatever. So I can't use kinetics. I can't use F equals to ma or F equals to 0 because I don't know that stuff. So the only other thing that's left to me is to look back at my kinematic equations, all right? And so I can go back, look at my kinematic equations. I have my final positions. I have my initial position. I have time. I have initial velocity. So I can figure out something using the kinematic equations. All right. So if you get lost, just think that way. What tools do I have to use? And do they apply to this situation? And just go through it. And that's going to require that you understand what's needed for each one of those sets of tools. Okay. All right. So homework is due before midnight tonight. I think I set the times right. Let me make sure before we head out, because I got an email and now I'm doubting myself still about that. But I think I set it for midnight tonight. It was just the wording that was off. Yeah, 11:59 p.m. tonight is when the homework is due. I had just put by class, and that wasn't right. I had copy pasted the instructions and just changed the date and forgot to leave out that part. So that's fixed, right? If you have any questions, let me know. Otherwise, have a very nice weekend. Get the homework done tonight, and that way you don't have to worry about physics for Saturday and Sunday. We'll see you guys on Monday.
Bye, sir. Have a good weekend.
You too.
Bye, sir.